All right, so here's an example of a linear transformation that's defined in terms of a matrix. So we've got a 2 by 2 matrix A. So that defines a linear transformation that goes from R2 to R2. So here's the header and here's the definition. You want to plug a vector x into T, just multiply it by the matrix A. So in part A, we're asked to figure out what T of the vector 3, -1 would be. So that's fairly straightforward. All we need to do is just multiply the vector by the matrix. So let's actually work this out. So T of 3, -1 is just going to be the matrix A times the vector 3, -1. And we can use the definition of multiplication to figure that out. So it's going to be 3 times the first column plus -1 times the second column, right? And then we can work that out. We're going to have 3, 0 minus 2, 1. So work that out and you end up getting 1, -1. So you could say therefore T of 3, -1 is equal to 1, -1. Okay, so there you go. We can also solve problems that ask us to go the other way. Like in part B, in this point, we're asked to figure out what the vector x would have to have been in order to yield the output vectors 8, 6 when we plug it into T. So we're given the output value this time, and we're asked to figure out what the vector x would be. So to do that, it's actually not so bad as long as you know how to start it. Just remember, start out by actually giving yourself something to work with. So let's write the vector x in terms of its coordinates. So we've got a vector in R2, and we want T of x to be equal to what? You want it to be equal to 8, 6, right? So that actually gives you something to work with, because T of x, let's work it out down here. So this is really just T of x1, x2 is equal to 8, 6. And you can replace T of x1, x2 with its actual definition. So this is going to be the matrix A multiplied by x1, x2. So we'll have this multiplication. And then once you get to this point, then you can see you've actually got yourself, this is a matrix equation, right? Here's your coefficient matrix, here's your variable vector, and here's your constant column. So this is really just the matrix equation of a linear system whose augmented matrix, we can just write it down like this, right? And if you actually just row reduce it, you only need to do one operation, just subtract row 2 from row 1 2 times, and you'll get it into reduced row echelon form. And I'll just fast forward through that. You're going to end up getting this. So that gives you a way to find the answer, because now you know that x1 has got to be -4 and x2 has to be equal to 6. So therefore you can say T of let's write it this way. We were asked to find x, so let's just write x as its column vector, x1, x2, and we found the values as to be -4 and 6. So that was fairly straightforward, and that was a quick one because this matrix wasn't too complicated, right? So in other words, this coefficient matrix wasn't too complicated. So when we got to this augmented matrix, there wasn't a lot of work to be done to row reduce it. So it was very quick to pull out the solution. But if you had a more complicated matrix, then this type of a question can be more difficult to answer. But the way you approach it will be identical. The only difference would be maybe you'd have some more work to do at this stage. Okay, and I want to mention something. Actually, we'll talk about the picture first, and then I'll come back up and mention it. So this is an example of a transformation. It's easier to see what it's actually doing if you look at a diagram like this. This is straight out of your textbook. This is a really nice diagram. Rather than showing us vectors, it's just you've got a 2 by 2 picture, kind of just dropped in the middle of the Cartesian plane, right up against the axes. So when you apply T, imagine you applied the transformation T to all the points in R2. Or in particular, how about, let's keep it simpler than that. How about you just apply it to all the points that are in this 2 by 2 box. Then what that would do is it would turn it into this slanted box, this distorted box. It looks like it's a parallelogram. And this is an interesting one because it's kind of like a stretch, but yet it's not so simple because there's lots of points on this picture that actually haven't moved. And there's lots that haven't moved very much, but there's some that have moved very far as well. So let's just actually draw a couple of vectors. How about I'll just draw, how about one here, one that goes right to the point 0, 2 on the x2 axis, and then I'll draw a vector that goes to this point here, and a vector that goes to this point here on the x1 axis. And let's give these names. We'll call them u, v, and w. And if you want to see where t maps those vectors or where it sends them, you can just look at the corresponding point on the picture. So t is going to send u to this vector here. So it's stretched it, it's pulled it horizontally to the right by quite a bit, by 4 units. So it's moved it a long ways. So this is t of u. And then t of v, the way we've labeled it, gets moved all the way over here. Okay, so this is going to be t of v. So that one's been pulled horizontally as well. Not by as far, but it has been pulled to the right. And, well, what else? And I shouldn't say not as far. Proportionally, it hasn't been pulled as far. So the x-coordinate of this vector, or I should say the x1 coordinate of this vector is 2. And it looks like it's been increased to 6. Whereas, so it's been tripled. But this one has an x1 coordinate of 0. It's right on the x2 axis. But if you look at the x2 coordinate of this vector, this would be around 4 here on the x2 axis. So this had an x2 coordinate going from 0 increased all the way to 4. And this one, oh, I guess actually I lied. This one is tripled, so it's gone from 2 to 6. They both increased by 4. But what the interesting part here is now the w. Look at w. T of w hasn't changed at all. That's the interesting thing about mappings like this. The answer is, why is it? Why did it move u and v so far, but it didn't move w at all? This is actually, I try not to spoil the joke here, but before I go any further, I'll tell you what these things are called, and you can, why do you think they chose a picture of a sheep for this example? It's kind of funny. This is an example of what's called a shear. So if you want a picture of a sheared sheep, if someone said, hey, I got a picture of a sheared sheep, you want to see it, you'd probably be expecting to see a sheep with no wool on it. But instead, they'll show you this picture. It's kind of just a cheesy linear algebra joke. But let's add a note and then we'll come back to the answer to this issue below. So this is T as an example of a shear. It's a shear in the horizontal direction. Okay, so let's just add that as a comment. Now, what is it about shears? How do they work? Well, if it's being sheared in the x1 direction, what that means is the vectors are being pulled in that direction by an amount that's proportional to how far away they are from the axes x1. So notice that the distance between w and the x1 axis is 0, right? Because it points to a point that is directly on the x1 axis. So there's no distance between w and the x1 axis. So because of that reason, it didn't get moved at all. It's the same vector after you transform it by t. But u and v, well, they're further away. They're actually, if you measure their distance from the x1 axis, their distance would be 2, because this distance is 2. So it's a shear in the x1 direction. And actually, they both were pulled over to the right by 2 units. This is just a fun fact. This number 2 is what dictates that. That 2 gets multiplied by the distance that u and v are away from the x1 axis to give you 4, and that tells you how far this shear t is going to pull those vectors over to the right.